In this video, I want to start with an example. I want to let the pk sequence be this sequence. I'm going to start with 1, 1/2, 1, 1/2, 1/3, 1, 1/2, 1/3, 1/4, 1, 1/2, 1/3, 1/4, 1/5, and so on. And what I want to notice is that this particular sequence is made up of a pattern of a 1, and then we go down a certain point. So eventually we will get to a 1, 1/2, 1/3, 1/4, 1/5, and all the way down to 1/10. And then we hop back up to 1, and we'll have 1/2, 1/3, 1/4, 1/5, all the way down to 1/10, and then 1/11, and then we'll hop back to 1, and so on. Now, there are several things that I want to notice about this particular sequence. And so I simply am going to write down a few facts that you can verify for yourself. The first fact is that for all of the pKs, they're all going to be less than or equal to 1 and strictly bigger than 0. The second fact is that the sequence of pKs does not converge to any x. So for any x, inside the real numbers. And the easiest way of seeing that is that if I circle these terms here, I see that every tail of this sequence, so every entail of my sequence, contains an infinite number of 1s, which would kind of point towards possibly converging to 1. But I also want to note that every entail of my sequence also contains, and here I'm going to circle something like these terms. We're always going to contain a sequence that looks like a 1/2, 1/3, 1/4, 1/5, and you can make this go down to whatever end you want. And this would be kind of indicating that we would be looking at 0 as a possible limit. In other words, it's possible to show that both 1 and 0 are accumulation points for my sequence. And that's enough to say that the pKs do not converge. And let me correct my handwriting there. But it's interesting to note that I can find what I can call subsequences that will converge. So let me just kind of think about that for just a minute. These elements form a subsequence. And that is a subsequence that is a constant subsequence and hence converges to 1. So at this point, I'm not yet going to formally define what a subsequence is. I'm simply going to note that this sequence contains an infinite list of 1s. But the sequence also contains this 1/2, this 1/3, this 1/5, this that 1/4, this 1/5, and so on. In other words, I can also clearly find, notational problem there. I should read k goes from 1 to n. This also contains an infinite list that looks like 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. And these two things are collectively called examples of subsequences. So informally, what I want a subsequence to mean, so let's kind of do this informal idea. Informally, a subsequence of a particular sequence is an infinite list of terms from my original sequence in the order they appear inside the original sequence. And I kind of want to make this a more formal definition, so let's look at that. The formal definition of a subsequence is this particular definition, that if we have two sequences, we call the second sequence, the Q sequence, a subsequence if there's a strictly increasing sequence of natural numbers in K, going in 1, in 2, in 3, and so on, such that the QK is equal to P in K. And it's typical that we're going to use this kind of notation to denote the subsequence. You should take the time to stop the video and copy this definition down into your notes. What I want to do is I kind of want to pick this apart on understanding what this fairly dense notation means. So let's again look at some ideas. So let's let my PK sequence be P1, P2, P3, P4, P5, and so on. If I let the sequence of NKs, which has to be a sequence of integers, let's let this be 1, 5, 9, 13, 17, and so on. This is every other odd integer. Then it would turn out that my subsequence would look like P1, P5, P9, P13, P17, the next one would be P21, P25, and so on. And so this is just a convenient way of picking out specific terms of the sequence. You should be able to understand this definition now and work with it.